So I'm delighted to introduce Rob Mahoney as our speaker this morning. Rob's from the Australian National University in Canberra. And Rob is the originator of one of the core algorithms been in ArduPilot the longest, which is the DCM algorithm for attitude estimation. He's one of the fundamental researchers in drones from way back. So Rob, over to you.
Cool. Let's just see whether that is that screen shared nicely for everyone.
Perfect, Rob. Yep, looking good.
All fine? Okay, cool, great. All right, so thanks, Tridge, for the intro. Let's see if I can get my computer working. I thought I'd just start because I'm not so much a part of this community. Just say who I am, as Tridge just said. So I'm a professor at ANU, and I lead a systems theory and robotics group here. And I've been working in aerial robotics technology now for 25 years, 22 years probably, since 1998, trying to make a helicopter fly. So as Tridge said, some of the work that we did back in 2005 or so was pretty fundamental in getting the DCM flying and sorry, pardon? I missed that. Somebody said something I missed. So that was sort of a contribution. This is, sorry, that's the volume from this from the video. Sorry about that. And so that's, I mean, that's a DCM running in the little video there that people are having a look on. So we did some of the early modelling work on quadrotor vehicles with one of my students, Pauline Pounds, who's still around in academia. And we've done a little bit of recent work, which might be interesting to people, on modelling motor control. So being able to model thrust directly from the motor. And so now that we're getting feedback, direct feedback from the motors, the ESCs, then that sort of work might be interesting to people. In particular, it's quite cool because if you get an updraft or a downdraft or something, the motor servo controls the thrust on the vehicle rather than actually just servo controlling the RPM of the rotors through measuring the electrical power into the motor. We did a little bit of work on optic flow-based methods, which sort of hasn't really crossed over into the hobby community. And we've done a little bit of work on GPS delay with Paul Risborough. So some of the way that GPS delay is handled in the EKF 2s and 3s, if I understand, are based on some of our work. And I've got interested recently in visual odometry, and that's, I guess, what we wanted to talk a little bit about. Let's see, a little computer. I've got to get used to everything running. So if I press this, does that. I should be able to start. So this is just a demo which I did of some work. This is Peter Van Goor, my student, who'll talk a little bit later and show a demo. And so this is your classic visual odometry problem. So you're using a camera. In this case, you can see it's just on a phone here, and you're looking at an object and it's seeing points, which you can see in the top right. And from measuring the points and looking at the way they move, it's recreating the actual trajectory of the robot moving through space. So if you actually think about this from the point of view of scale, so here we're quite small and we're quite close to what we're looking at. But if you imagine multiplying all of the scales by 10, then that would be very similar to a vehicle flying over some sort of relatively flat sort of surface. And I guess that's the algorithm that we'll at least show to you. So what I was thinking is worth talking about today, and I don't know, I'm not so much a part of this community, but it's certainly super exciting to be part of these conversations. What I thought is, rather than talk in detail about the algorithms, I just wanted to give a little bit of a high-level view of what is visual odometry and what are some of the challenges, and why perhaps it's not an obvious case that we can take the research results that are out there and put them onto ArduPilot and expect things to work, and what we might need to do to make a really effective visual odometry system for the open source community. And so hopefully I can sort of cover a few of those bits and pieces, then show Peter and Ryan can show a few results, and also Jim Radford I saw was here, so hopefully I'll invite him up, and he's the guy who's done the development work on the RealSense T265, and I know that's one of the systems that's being used pretty heavily in the community, so we can ask a bunch of questions to Jim. So basically, odometry is the idea, this ability to infer relative movement of a vehicle from the sensors, and visual odometry then is when you use a vision sensor. And the point here is that it's a relative measure, right? So the key idea is that you're measuring something relative to some origin. And so this is a little bit different from having a GPS system that's giving you a world origin or something like that. And so this idea of exactly what is the origin that you're measuring with respect to, and how do you choose the origin, is one of the key questions that comes up when you try and use this sort of technology. And so I'll talk a little bit about that. So just so that we're all on the same page, I thought I'd do some really sort of fundamental definitions to describe what we're doing. So I'm interested in some sort of flying robot, which we've got over here, and I'm going to describe its position in space, or its pose, by two parts. So one part is a displacement, or a position, and that will be relative, as I said, to some origin. So in general, when you're doing visual odometry, you don't get given that origin in advance, you just sort of pick this. So this is some arbitrary choice. Okay, and so then it's just a displacement in the three axes for that, and then an attitude, and I don't really mind how the attitude is expressed, but the mathematics is easiest is if this is expressed as a direct cosine matrix. So this is some sort of cosine matrix or a rotation matrix. And so those two things combined are what we talk of as the pose, okay? And so it's an interesting question, actually, why a lot of the filters and such like for aerial vehicles are built where you separately filter for position and you separately filter for attitude. So you have an attitude filter, they might be coupled, but really you're thinking about this as two separate sort of filters. And the reason why in SLAM or SLAM or visual odometry that you really need to treat these as a combined object is because when the robot moves, the way that you observe the world moves as a combined function of the two variables. And so you really need to think about pose rather than separately doing a displacement filter and separately doing an attitude filter when you start doing visual odometry. All right, so the idea is that you're going to put a camera onto some sort of vehicle. And so you've got two sorts of measurements that you're going to be deriving from a camera. So one of them is something like a feature. So that'll be some point in the environment, like the base of a tree or a branch or a corner of a road or an edge of a building or something like that. Which the actual feature points have some sort of high contrast, usually what we call a corner in a feature. So either that or some sort of patch of pixels or something that's recognizable in the image. And I'll show you a picture in the next slide about that. And so then you also can get other things like the horizon is another very common thing that people pull out of images. Sun bearings, if you are actually looking at the sky and you can see the sun, then that's pretty easy to pick out. And let's not forget that if we've got an IMU on board, we can start doing things like gravitational estimation. We can have attitude filters running just from the IMU, and they can be coupled into the filter as well. It gives us a bit of an idea of what we're doing. So this is some work that I'm doing with my student Peter Van Goor, and this is actually from one of Tridge's disco parrot flying over Spring Valley Farm, which is one of the ANU field robotics. And you can see what the features look like, right? They pretty basic, sort of tiny little image patches. So you can sort of, if you look at a spot where there's a bit of an edge here, you can see, for instance, that feature there that I've just circled. It's a bit of shadow over a piece of grass. So you can imagine there's a sort of a dark corner and a light sort of U shape around it. And that was clearly enough for the image algorithm to match between the previous frame and the present frame. So here we only see the latest frame, and the actual feature that's identified, I believe, is actually the red dot, and it came from where the yellow line started. So what we're seeing here is feature matches across 2 frames, but we're only visualizing on 1 frame. And so you can see one of the characteristics of what you're actually going to see. You see an awful lot of stuff on the horizon, right? Edges, bright edges like that are very, very easy to pick out on the image, but they're not much use, right? That horizon is a good 5 or 6 kilometers away, and it doesn't really matter what the plane does. It's not too bad as a bearing, as a direction, but it's not very useful for actually measuring any sort of displacement, okay? The stuff that's really useful is the stuff that's down here close to the vehicle, because it tends to move the most when the actual vehicle moves. And so here we're not doing too badly because we've got a few, quite a few matches reasonably close to the vehicle. But you can also see some of the difficulties, right? So you can see where there's false matches over here where the algorithm has failed to pick the actual translations. And we've done quite a bit of post-processing here, if I remember. Peter can tell me more in a moment, but we've sort of cleaned up as much as we can of the false matches. You can also see over here, we've got a few false matches, particularly around the edges of images where you get distortion from the lens, so lens distortion, so your motion models start to fail, all of those sort of things that cause you problems. All right, the other thing that you can see here is that we've got quite a lot of features here, so something over between 100 and 200 features. And that's a characteristic of what we're trying to do, get a density of features that allows you to get sort of a robustness to mismatches. And that's something that we'll talk a little bit about. Okay, so each one of those features, each one of those measurements of a direction is associated with a point in space. And so the way that we typically do that is down here in the corner. So you've got some arbitrary frame of reference that you've picked. And you represent the position of the robot with respect to that. So you've got an attitude and a position of the robot, and then you separately represent points in the environment with respect to the same frame of reference. And so you're going to collect together all of the points in the environment and the pose of the robot and try and unify these all into one sort of framework and use that to measure the position of the robot changing. So this is what I was saying here. So the state of your system, so what goes into the state of this filter is a pose, right? And a set of points. So these are somehow in the environment, and they're all measured relative to some arbitrary frame of reference here. You've got some point out in the space and then what you actually measure. And the point about a camera is you don't actually measure the actual position of the point. So the best you could ever do with an onboard sensor is measure its body fixed frame position. With a camera, all you can do is measure the direction. So you can see here in this equation, basically this is the body fixed frame point, and then normalizing the direction. You can think of that as being something on the sphere or on an image, the direction, and that's actually the measurement that you get. And that means that you lose depth information in the actual measurement. It has to be recovered from triangulation. All right, so visual odometry and a thing called simultaneous localization and mapping are essentially very, very closely related. And so the idea is that the simultaneous part, whoops, sorry about that. The simultaneous part of this is the idea is that you're doing both mapping and localization at the same point. So if you think about mapping, you have an environment that you don't know, and you're looking for and finding these features out in the environment, right? And what we'd like to be able to do is actually build a map so that we know relative to some inertial frame, wherever I happen to choose my reference frame, we know these measurements, these PIs, right? Now, if I know the PIs and I move my robot to a new position, right, and I measure the same points from the robot, then I can use the matches between the environment points to infer what the translation between the previous robot is, the previous robot position and my present robot position. And this really is the odometry, okay? Or in this case, it's the localization, the way it's written there, okay? So similarly, if I knew odometry, so if I had, you know, GPS, you know, one of Paul's EKFs working perfectly, then I could use the offset of the motion to triangulate points in the environment, and then I could build a model of my environment, right? And the difficulty is that these two problems are very closely linked. So if you know the map, you can derive the robot pose. If you know the robot pose, you can derive the map, but combining the two is a simultaneous problem, and that's a chicken and egg problem. And so that's where a lot of the complexity of the mathematics in visual odometry comes from. So I wanted to actually talk about this a little bit more, because I think it's actually a really important thing for ArduPilot to understand. So if we start with imagining a reference frame, and we've represented the robot with respect to that reference frame, there's this thing called gauge invariance, which sort of is the killer that comes from this same problem. So there's nothing unique about this reference frame, right? If you're just doing visual odometry, you have no God up there that gives you the correct reference frame. If you've got a GPS turned on, you can reference that back into the northeast down coordinates of the GPS. But if you don't, then you could make any arbitrary change of reference frame that you particularly wanted to, right? So you can put that reference frame anywhere you want to. And by transforming the variables in your filter, you can do that online and change references however you want to. So in particular, one of the things that you could do is simply change the reference frame all the time so that it sits exactly at the origin of the robot, right? So if my reference is equal to my robot pose, right, then my robot pose is always 0 attitude, the identity attitude, and 0 displacement. And that is perfectly viable from the formulation of SLAM. There's nothing at all stopping you re-expressing the coordinates all the time in that point. And what you'll get then is basically the egocentric or body fixed frame representation of the environment, okay? Now the point I wanted to make here to understand is that this is part of what a SLAM solution is. So a SLAM solution is entirely compatible with this representation. And yet, if you look at this, then this piece of information from the point of view of visual odometry is completely useless, right? It doesn't give you any useful information about where the robot is. And so this sort of is, in a sense, part of what really underlies the challenge in getting these systems running on in an open source community, right? So in addition to running classical SLAM type algorithms, we need to ask the question, how can we choose the reference in real time on these sort of aerial robotic systems? So if we're coupled up with the EKF running, and if it has some reasonable input into it, then there's no reason at all why we can't couple the solution of the EKF back into a VO algorithm so that we never get these resets that we were talking about yesterday when I think Randy was asking that question about how do we couple it. Of course, in order to do that, we need to have the VO code running in real time, because that would be an innovation that goes into the VO code. So similarly, there's some questions around, can we use some keyframes and global optimization? So I won't talk about that. But this final point, I guess, is the one that the situation where you probably can solve this reasonably well is where you get what we call loop closure, or critically visibility of the same landmarks. So if, for instance, you're using visual odometry during a takeoff scenario, so where you take off and then you loiter over the same environment where you continue to see the same points, then we've got a chance of solving this, right? Of basically being able to lock down a fixed reference in a sensible way. Failure to fix a reference is where you get drift. And so when we talk about drifting solutions of visual odometry, really what's happening is it's the reference frame that's moving around in space, okay? And because the reference frame moves, your odometry solution is moving both with the reference frame and the movement of the robot. So that's what means that you then get information here which isn't so useful as a measure of how far you've moved, okay? Even though it's still compatible with the overall problem. So I guess I wanted to just say a couple of things about why I also think this problem is hard. If you go into the robotics literature, at least, what you'll find is that SLAM is considered a solved problem. It's just that actually applying a SLAM algorithm that works reliable on aerial vehicles sort of doesn't exist. Although maybe the T265 is actually getting there, and I've you know, we've got Jim along, so he can talk a little bit more about that later. But the question is, why don't sort of academic SLAM algorithms actually work on these vehicles? And it's got to do a lot with why academics do work, or what they're measured by. So there's these metrics which are standardly used to evaluate the performance of SLAM and visual odometry algorithms. And they're not actually very good at measuring the robustness of the algorithm with respect to running on crappy hardware, right? So academics developing these algorithms are trying to get something that has very, very good performance, but they're not necessarily trying to optimize the algorithms to be able to run on these sort of open source platforms and hobby platforms. And that's, I guess, what I'm interested in trying to do in this piece of work, working with this community. And so some of the things that come up there, and I won't spend long on these slides because I think it's all obvious, but clearly we're going to be wanting to use relatively cheap and simple sensors. So we're going to get motion blur, low dynamic range. You get all sorts of things with rolling shutters. We don't know exactly when the photo was taken, so we've got shutter timing issues, we've got bad calibration, and probably low frame rates, okay? So small field of view vision sensors, so fisheye lenses are heavy. I think this is something where we really need to think about the hardware. You know, probably really do need large field of view to do reasonably good.
What do you mean by heavy? This is Jim, by the way.
Yeah, it's because fisheye lenses, they need to bend the light a lot. And so generally a good quality fisheye lens, or a reasonable quality fisheye lens, is made of glass. And so they do tend to be quite heavy, whereas most of the cheap cameras, they have the plastic lenses. Does that make sense?
Yeah, I just didn't know if you meant conceptually heavy, like they were expensive to deal with, or if you meant physically heavy.
No.
Apparently you meant physically heavy, yes.
Kilograms. Well, grams. But yeah, no, the lens on one of these things is typically heavier than the camera. I think that'd be true to say. That's said off the top of my head, but I believe it. It's always good to believe your own statements. So noise in pixel locations. So features aren't very well defined objects, and so exactly how do you talk about a feature, and that's a really important thing. Aerial vehicles move fast, and in particular the angular velocity. So you've got this real issue in when you do a fast correction of angular angular position or attitude, how do you actually track features through that? And that also couples into one of the weaknesses of most VO algorithms. So that's actually the standard failure rate of most VO algorithms is in rotation and translation. So when you get high rotations, that's the normal failure mode. When objects move in the environment, then of course you no longer can identify them as constants. Aerial vehicles have lots of occlusion, sort of horizons, ground, trees, and lots of range of depth. So you might be flying only a few meters above the ground, but you're looking at the horizon, which is kilometers away. So that's a problem. And you need to put it on a limited processing power. So the big issue is the one that I mentioned earlier, so data association. And this is an interesting point in existing algorithms. So most classical algorithms that you take off the shelf from the community, they use optimization methods to get the performance. And so when I say performance, they're really looking at getting, minimum root mean square error of whatever the measure is that they're doing, whether it's the map quality or the trajectory. And as a consequence of that, they're really optimizing locally around the true solution. And these sort of mismatches are very, very bad for those algorithms. So those algorithms generally operate on some sort of linearization principle, and they're operating on some sort of Gaussian noise type principle, okay? And so bad data associations are not Gaussian. And in particular, they tend to break these optimal type methods. And so the classic approach in the literature is to take your data association matches and run a whole bunch of algorithms to remove all of the data association errors. So you treat the data association errors not as part of the actual optimization algorithm, but as a separate data processing procedure where you remove the bad data and then you run an optimization algorithm after that works quite well. And so the problem there is that a lot of algorithms spend more time, they might spend 60 to 80% of their time actually removing data mismatch, okay, depending on the situation. And in particular for us, we're looking at situations where there might be quite bad sensors, and so data mismatch is even more likely to occur. Again, this is just a guesstimate based on some of the work that we've been doing. And I guess I'll finish up really super quick with a simulation we did to sort of demonstrate this. So this is a very simple little example where we're driving, it's a simulation actually, but we're driving a mobile robot around in a square. So it basically drives along in a square here, drives up, drives along and drives back down here. And it's measuring points. So each one of these little pluses and a cross, if you look there, the plus is I think the true value, and the cross is the best estimate that the filters managed to acquire for it. And so what we did was a series of experiments here where we added data association. So all of the measurements are noisy, so we add Gaussian noise, but we also add data association noise. And what you can see here is an example where we're doing a very simple, this is a similar principle to the old DCM filter that I derived about 15 years ago. So very, very simple first order gradient-based observer. And this one here is an optimization-based Kalman filter. And so what you can see is by adding in the data association, essentially the Kalman filter is starting to fail. And it's because each one of those data association errors is actually adding non-Gaussian noise. So it's adding something outside of the performance of the Kalman. And I guess this is just to demonstrate the same result. So what we're doing here at the bottom graph is just showing an example where we've added the probability of mislabeling a point, right? So down here, everything's perfect. There's still noise in the system, but all the data association is perfect, okay? Up here, 1 in 5 points is mislabeled, okay? And what we've done is we've done an EKF in blue, and this simple sort of first order, very basic filter based on symmetry principles in green. And you can see here when things are perfect, so this is 0% data association. The Kalman filter is here on the right, and it clearly outperforms what we're trying to do. And that matches what we expect, right? So this is the correct mathematics for that particular assumption. What we can see here is when we get up to 3%, so this is 1 in 30 data association errors, then you're starting to see the Kalman filter performance degrade. And this is because we're feeding into the Kalman filter, you know, errors that are not associated with the Kalman filter. And so this sort of robustness that's associated with this question is something that I really think needs to be tackled in the algorithms that we deploy in these sort of scenarios. And I guess the other thing is that the particular filter that we're doing is very low compute. So we can, because it doesn't carry around a Kalman gain matrix, we can run up to 200 features without imposing too much on the error or the processing time. So this is both memory and processing time scale with the number of features. All right, so I've taken more time than I was planning, so I apologize for that. But what I thought we could try and do is I wanted to pass across to Ryan to quickly show you the environment that we're trying to set up. So we're trying to set up with Tridge this AirSim environment in Cittal. And I thought there was an opportunity there to get him to just talk about that and show you what we're trying to do so that we can test some of these things. And then Peter was going to talk quickly about the algorithms that we're doing. I've taken too long, so I'll get out of the way in a moment. And we've also got Jim along, I saw. So hopefully then we can have an open discussion. So Ryan, are you there?
Yeah, I'm here. Hello, everyone.
Cool. I'll how do I have to get out of my open screen. How do I stop sharing there? Enter. So there, I'm out, and now I go to Zoom, and I don't want to join a meeting. Cancel. I want to. Where's my Zoom? Here it is.
I've just turned off your sharing for you there, Rob.
Oh, thank you. All right.
Is that showing my screen now?
Yes.
Okay, so I'll be pretty quick with this then. I'll get more faster to the demo. So essentially what we've been working on is trying to recreate a realistic environment so that when we develop our visual odometry algorithms, we can kind of integrate them a little bit easier into the kind of ArduPilot code base. So I guess it's kind of a two-pronged approach with these simulation environments. If we can try and replicate the kind of physical setup that goes into the, you know, ArduPilot talking to the drone and whatnot, then we have easy integration. And then also there's, you know, lots of time and risk that's usually associated with field robotics, things like hardware failings. And, you know, when you go out and collect the data, it often takes a lot longer than what you'd expected. So trying to speed up the actual algorithm development is another thing that we were looking at, which I think we fully realized in the last 2 days when we were trying to set this up properly. So essentially the way that it's pretty simple setup. So the ArduPilot is talking through a Cittal port and sending rotor controls to AirSim, and then AirSim over this Mavlink.com C++ class is sending the sensor messages back to ArduPilot. So AirSim essentially has 3 different streams. The AirLib is responsible for the physics engine. It's responsible for the sensor models, so you can get IMU, GPS, baro, and the camera. There's also different vehicle models and control models. And then the Unreal provides kind of the environments that we will be using, and also, you know, the rendering and shading packages and things like that. And then, yeah, the Mavlink.com is essentially set up to send messages to Mavlink devices. So I will just jump straight into the demo. Let me just get this up. Just quickly, is this showing in a JSON file right now?
Yes, it's showing the config for AirSim.
So essentially, this is how we kind of parameterize the simulation. So down here, this is the kind of ArduPilot interface. So here we're using an ArduCopter. You can also use an Ardu rover as well. And there's also multi-vehicle simulations too. This is the kind of port for receiving the messages, and then this is where we're sending our rotor controls. And then on the AirSim side, we're kind of setting up a forward-facing camera in this setup. And then you get to control things like the resolution of the camera, the field of view, exposure speeds, things like that. And then you can also inject noise as well. Yes, so there was actually a lot of playing around in this kind of setup, turning off compression, having the view mode no display, because there was a kind of problem with the actual frames per second. It's the AirSim API is a little bit slow, and so trying to essentially turn off all rendering except for the ones that you need was just necessary in getting that set up. So let me just go to terminal here. Okay, so I'm just going to run. Is it showing a terminal, Tridge?
Yes, we've got the terminal running.
Okay.
AirSim script about to run.
Great. So I'm going to first run the, this is a pre-compiled binary, again, for a performance boost. I'll talk a little bit about the environments afterwards. So that should get that set up. Then I'm going to run the sim vehicle here. And then, okay. So, and then lastly, this is the AirSim script that essentially pulls the image data from the forward-facing camera. So let me just go to that. So this is kind of what we're seeing in the landscapes environment. Is that coming up?
Yep, lots of snow.
Lots of snow. Okay, great. And then also you can see from here, I'll just show you. So this is what the console is showing from ArduPilot. And then also this is what the map is showing as well. So everything is all working smoothly. Now, let me just go back to the forward-facing camera. So this is running at the moment at 14 frames per second. And so I'm just going to take off here. I'll do this quite slowly because I assume it's going to be... Is that moving? Someone?
Not yet. Doesn't seem to have taken off yet. Is it armed?
Yeah.
We'll need faster.
How's that?
Now it's taking off. Yes, now we've got takeoff. Great.
All right. Is it lagging or what's it like?
Oh, it's fine. It's just displaying it taking off. It's probably 30 meters above the ground. And we're starting to see the valley.
All right, I'm just going to put it into a loiter and just start moving forward now. I can speed that up.
It actually looks quite good, frame rate wise.
Okay, cool. Yeah. Okay,
Still
so
need faster computers.
Yeah, I think that was definitely a problem that we were facing, is the actual frames per second.
You're
But
running
yeah,
this on a laptop, aren't you?
Yeah, running this on the laptop. So this isn't some bespoke kind of box that I've got here. It's just a HPNB. So there's definitely room for improvement in that regards. But as you can see, we're flying along. The way that we're collecting these images is we are picking up the timestamp that's associated to it, and then we can ultimately put this straight into kind of an image algorithm. But what we've done for the purposes of this, and what Peter will kind of talk about, is we can save these images, save the timestamp. We can also run the IMU API. So I'm also collecting that at the moment, and that's running at about 3 kilohertz. But I've kind of put that down to about 300 hertz, just for Peter's stuff. And yeah, this is pretty much it, right? Like, you can fly around. You can actually also plug in a remote control and use it that way if you'd like. And then you also have a range of different environments. So there's the standard blocks environment, which everyone gets access to. So there is a on the ArduPilot website, there is a setup for that, for getting the blocks environment running. It's not exactly trivial getting these landscapes and different ones running I think with the AirSim maintainers starting to move a bit, I think we'll be able to get more easier access. And Rob has just linked us to one of those a paper that was recently released on using this more for drone racing. And I think if those binaries are released, it'll be easier to get a hold of these environments and use them. And as you can see, if I just switch to the map here, you can see the copters moving along merrily. Yes. So pretty much limitations at the moment from my computer is just, you know, the frame rate. It's not exactly ideal. We had it at 30 frames per second on the blocks environment, but obviously with these new kind of shaders and stuff in this kind of richer environment, it drops down a little bit. There's also some things with environments and licensing if we want to release the environments to the actual ArduPilot community. It does say that you can share the environments if you buy them with your team. So I guess we can just say that our whole team is the ArduPilot community, hopefully. But we'll see how that works. Yes, so we can.
Cool.
That's about it from me.
Thank you, Ryan. Do we? I think we might just zip on and get Peter to show us running the VO solution.
Sure.
So we can get through to Jim and open questions. Peter, can you?
Yep, I'm here. Can you hear me?
Yes.
Yes.
Cool. And see you as well.
I will share screen. Desktop. There you go. All right, so you can see my slides. Great. So I'll skip right past the first demo in the interest of time. I just want to talk a bit about how it all actually fits together, right? So as Rob talked about, we have this VO or VSLAM algorithm. And what it does is, well, from this perspective, it takes in a linear velocity, an angular velocity, and some collection of image features that are being tracked. And it spits out a vehicle position, an attitude, or pose, and some environment points. But to actually use this in a real system, the questions you need to answer are, how are you going to get image features, and how are you going to get linear and angular velocity? Because depending on your vehicle, these are really non-trivial questions. So image features are relatively straightforward. You can use an image feature detector, and there's a whole literature out there on how you can do that. And all it does is it detects points of interest in the image. So this is an image from one of Ryan's simulations, and I've just marked out a bunch of image features that are being used in my algorithm. Yeah, so all you need to do is get an image, and what we'd like to do as well, because we're doing this continuously, is we don't want to detect features that we already have as part of the state. So that's a detail in the implementation of that. And then you need to track features. Sorry, I'll move this out of the way. Okay. So you can see in this picture, the red dots, the red circles are where the features are now, and the yellow lines are where they've come from. And so to do this, you need to have the previous frame, the current frame, and the features as they were in the previous frame of the video. And one of the difficulties in this process is actually determining when you've lost a feature. And that can happen in a number of ways. First of all, of course, if a feature goes outside of the frame, then you're no longer able to see it, so it's gone. Another possibility, though, is that the feature moves behind something inside the image, which is generally a bit harder to detect. And another problem is if features change because of lighting changes, or the local the local image around the point changes. And that's something that's also more difficult to detect. Okay, so this answers, in a way, the question of how do you get features and how do you track those features. These feature trackers, there are a bunch of standard solutions for as well. But how do we get velocities? So we built a velocity estimation system which uses the motions of the features, so those little yellow lines showing how the features have moved between images, to estimate the velocity of the vehicle between 2 frames of the video. And if you have measurements of linear and angular velocity, you can use those as well. But if you only have one or the other, you can still use that to improve your estimate of the linear and angular velocity. So for example, on a quad rotor, you typically don't have a very reliable linear velocity, but you've got quite a good angular velocity estimate from the IMU. So that can help you get a better linear velocity estimate. Okay, and this is just a block diagram of the whole system. As it is currently in my code, the key thing to notice is that ultimately we don't use any linear and angular velocity estimates at the moment. We're just taking in an image and eventually spitting out a vehicle pose and environment points. And to drive that home, I'll show off a demo. So, videos. Here you go. Hopefully everyone can see the video. Can someone confirm that they can see this?
Yep, can see it fine.
Great. Yeah, so in the top left, you've got the actual video stream from the simulated environment from Ryan, with the red points and the yellow lines being what's being tracked. You've got the estimates of the environment points and the robot pose, as well as its trajectory in the main screen. So at the moment, I haven't added in ground truth trajectory into this visualization, but I hope that for the most part, it's easy to see that the tracking matches reasonably well what kind of motion you expect in the window on the top left.
Now you don't have scale, correct?
Yeah, so that's the other problem with trying to draw the trajectory at the same time as drawing the estimate from the VO algorithm. So I've just spun it around a little bit so you can all see what the global trajectory looks like.
If you got ArduPilot to fly like a big figure 8 or something, that would make it easier to match up.
Yeah, for sure. That's something we should do as well. But actually, I'll talk about the issues in the algorithm at the moment. First of all, feature detection and tracking are the most expensive operations we're doing in our system at the moment, because you need to do image processing, which is it's a lot of repeated operations on little bits of the image. So you can reduce the cost of that by using a low resolution image, but then you have a low resolution image, so it's less accurate. It's a trade-off. Velocity estimation, the velocity estimator we've got is not very robust to outliers. So this is the problem Rob talked about before. We're using at the moment a reasonably traditional algorithm for the velocity estimation. And yeah, it doesn't respond well to features that are tracked very badly. Then the equivariant algorithm, the actual algorithm that we've developed, doesn't do as much as we'd like it to improve the position and attitude estimates. But as to the fourth point, this is really got to do with the gauge and variance problem that Rob talked about before. That ultimately you can choose any reference frame you like and it's all valid. So it's hard in that way to create an algorithm that does a really good job of pose estimation when everything is relative to your reference frame, to an arbitrary reference frame. And that's why the local estimation of the algorithm, so the local velocity estimation of the algorithm is quite a bit better than the global estimation of the full trajectory. So as to what Tridge said about flying at figure 8, I expect that the local curve that the robot flies according to our algorithm will be reasonably accurate, but I wouldn't necessarily expect it to be very accurate in actually drawing out a figure 8. Okay, so thanks. I said questions, but I don't know if we're ready for that yet. I'll go back to Rob.
Cool, thank you. I guess I also had invited Jim along. So Jim presently works for Intel. I believe he's actually about to become a free agent. So, but he's had a lot to do with the development of the RealSense. I haven't actually had a chance to exchange many emails with him over the last week. So Jim, do you want to have a quick chat? What would you like to do? Hey, Jim.
Yeah, you're muted, Jim.
Hi. I thought I could just tell you a little bit about the T265 if you haven't already seen it before. Let me share my screen, see if that works. Can you see this?
Yep.
Great. So the T265 tries to address all the issues that Rob just discussed. It's got fisheye cameras to deal with the field of view issues. It's got an IMU so we can get scale. So we have both stereo cameras to get scale for close things and the IMU to get scale for large things. So generally the problem with mono cameras is you can't really figure out the scale. But with stereo we can do it, and with the IMU we can do it. We started off originally on the iPhone 4S back in the day. This algorithm comes back there. And it was a mono, low res image with an IMU. It was the first camera that had that. Over time, this has grown to work with stereo and to work at faster IMU rates, and now to be a fully embedded solution that you can buy. We've worked really hard to make it low latency. So it's only 3 or 4 milliseconds latency. It's a 200 hertz output. So we're at the speed of our gyro. We run the accelerometer at 63 hertz. We run the images at 30 hertz currently. I'll give you see if I can give you a demo of the actual algorithm running. I don't know if you could see this. Please tell me if you can or not.
Seeing the slides at the moment. Seeing the
Let me try again. It made me choose a window rather than just going where I went, which was a bit annoying.
Yep.
Let's see about this one. All right, can you see this one now?
Uh-huh.
All
yep.
right, so
yep.
This is the same sort of setup that we saw before. This is going to be a drone flying. You can see, I don't know if you can see this in real time, but these are the features we're tracking exactly the same way that Rob was discussing. We actually have stereo, so I can switch back and forth between the left and the right. That might be a little slow, but you should be able to see it. We do many fewer features than Rob was discussing because it's an embedded low power system. We have to deal with all the same issues with matching features and these sort of things. Rotation is challenging, especially if you go quickly. So if you buy this device, I recommend not rotating. It's not that we can't do it. It's that we're much better if you don't. You'll have less drift, etc. So you can see we're reconstructing the path pretty reasonably here. And so that's pretty much the summary. It's the same exact problem that Robert was discussing. We track little features, we integrate them over time. We currently use a big common filter. So we have a monster EKF where everything goes in, the IMU goes in, the features go in, etc. We do have the scaling problem, whereas this gets bigger and bigger, it scales with n cubed, which is horrible. So we're limited computationally. So over time, we've used fewer and fewer features. When you run this on an x86, you can run hundreds of features. When we run it on the embedded system, we run significantly less than 100 states total, including the features and the IMU states, etc. So we're estimating the IMU biases, we're estimating the position and location of the device itself, and we're estimating the locations of where we detected features over time. So there's kind of a bit of a mini bundle adjustment going on. But it's all inside the EKF. So it's very similar to the systems you're probably already running to estimate your attitude and position, etc., to estimate your velocity, your linear velocity and angular velocity, etc. So we have all of those in there. All of them are in the big common filter. We have accelerations. We're also estimating acceleration as well as velocities for both rotational and linear. And that's pretty much it. We've done our best to, output this out the USB as quickly as we can and as low latency as we can. We don't do, as Rob was discussing, optimization because that's slow and latent in general. And so we process things as fast as we can, as quick as we can. The algorithm's generally asynchronous. We get in IMU, they can run at different rates, but they're at least all on the same clock. So one of the problems when you build this stuff yourself is getting time synchronization.
Yeah,
right? Getting good, accurate IMU data, and accurate time synchronization. And if you were to use this system, for example, at least that part would be solved. You don't have to use our algorithms. Instead of just taking our pose, you can just take the raw data and try to run your own algorithms on it. But at least in that case, you get nice time synchronization.
Yeah.
A lot of people try to synchronize everything so that the IMUs, the rate is the same as the image rate. We don't do that. We run completely asynchronous.
Asynchronous, yeah. Cool.
So
super. I don't have anything more to say, and we got Jim here, we got Peter and guys. Tridge, do you want to see about questions and whether people want to?
Yeah, so there's a couple of questions that come up in the chat. I'm also very interested in the possibility of us running like an experimental system, a new system like Peter's one, in parallel with the existing algorithms on the T265. So could we have the image feed? We can. Yes. So it's 30 frames a second.
Unquestionably. Yeah.
Yeah. So that comes out over USB. Is that correct? The 30 frames a second.
That's correct. Image? USB 3 if you want to get everything.
And that's time stamped, isn't it? As long with
correct.
the.
That's correct.
Yeah. So we should be able to then run using basically the same image data and run two different algorithms to get a comparison.
Yes.
Because the 265 is the baseline that really in our community, it's the reference that we're all comparing against. But for experimental stuff, that's great. And what are there ways in which ArduPilot's extra sensors, because ArduPilot knows it has bias estimation and things that it can do because it has additional sensors. Could it provide additional information to the T265 to assist in its?
Yes. So we support a odometry input currently.
Mm-hmm.
So for example, for wheeled robots, we'll allow you to send in wheel velocities, mm-hmm. right, to sort of reduce the drift, especially around bumps. When you rely on the accelerometer as much as we do, and we do, it matters significantly if you get to bumps. We just haven't solved that. We haven't spent much time at all on it, and we blow up often if you go over bumps. And from the drone perspective, also. We get scale from the stereo when you're close and from the IMU, but when you're up high, the stereo's no good, right? Yeah. Your baseline is so large that it's not useful. And so we'd only get scale from the IMU. And so you really have to work on vibration isolation in order to keep the accelerometer measurements less noisy, because we do rely on that so fundamentally in order to get this. But to address your point previously, the best thing you could do is record our data raw and then run all your algorithms all day on it. Compare our pose to your pose, etc. I mean, we're not perfect in any way. We'll have plenty of problems, but at least we're also running mapping on top of this. So if you look to the left and look to the right and you come back and you see the same features again, we will recognize them and attempt to make your pose similar to what it was last time we saw that. So the algorithm that Robert just described, if you go look to the left, look to the right, lose all your features, look back to the left, the odds of you being back at the exact same pose are nothing. It's more or less Brownian motion every time you come back to that same pose. And we've put quite a bit of effort to create a map of all the features we've seen over time. Now, of course, we've run out of memory. It's an embedded system. We don't have a ton. Algorithms aren't particularly optimized at this point to deal with a large map. But if you stay within a small scale, we can make your pose pretty robust to going in circles multiple times, et cetera, et cetera. I mean, so we'll eventually lose track, but.
Do you output the map as well? So is that part of the data?
Yes, we do actually output the map as well. We currently haven't opened up the format of the map. That's internal discussions that we were having. So we'll see if that ever actually makes it out. So we currently output a binary blob. I guarantee Tridge could fix, reverse engineer it in 15 minutes. Like, it's not complicated. We have not obfuscated it, right? It has what you'd expect: image patches, poses, and no, edges, right? There's no magic there.
Yeah.
So regarding the angular velocity limit, you were saying, don't rotate too fast.
Yeah, that's only because, so in
constant?
terms of, what do you mean a constant?
I mean, is that the same rate as it depend on the environment? Because what we do with our optical flow, for example, is the EKF tells the flight controller, the navigation controller, what limit there is in, what limits it should provide to navigation to allow the optical flow to maintain lock. So could we actually get feedback?
No, we don't provide feedback. And the limit is because our features are not rotationally invariant, actually. So we just have to keep creating features over time, and the more features you create, the more drift you're going to have. If you could track the same features as you just sit there and spin, which you obviously should be able to do, and we would be able to do were we to use rotationally invariant features, you would never drift. You would just sit there and spin. But because we don't do that, and you might have seen this in my video, when the drone rotated, we ended up losing the features after 30 degrees or 45 degrees, maybe 90 degrees. Okay. Oh, it's okay, we'll find new ones and we'll keep going. It's not a problem, like, fundamentally, right? I mean, every time you take a step forward or scale up, right? The features you see when you start on the ground are not the same features you see when you're 30 meters up, right? And we constantly see new features as you go through the environment. But the more you have to do odometry, integrate your equations going forward and rely on that, the less accurate we're going to be, right? If you fly low over the ground and try to add up the motions, it's going to be horrible. If you go up high and fly, we can see the same features the whole time, it's going to be great.
What I'm wondering is, can we get some
Jim,
data?
It's Paul Riseborough. I was just wondering about this scaling issue as you get higher. If you're looking down to the ground and you've got a laser rangefinder looking down at the ground, actually giving you range to ground, if you were able to incorporate that information into the solution, would that be
we would trivially be able to incorporate that into the solution if you could give us the range to the same range, is that you don't always have a point at which you're aiming at.
Yeah, but we could have the rangefinder bore sighted with the camera centroid, so at larger altitudes.
Oh, yeah, then that would be perfectly fine. If we could say that, over this image patch that I have the range here, and if I had features in that realm, then we would 100% be able to use that.
Mm.
Yeah, so I mean, the thing is, we have it's a big old EKF, right? You can throw in any kind of measurements you can think of.
Yeah.
You could add in anything else, right? We add things in all the time. Oh, let's try using this. We get depth from a depth sensor, right? Intel makes these little depth cameras, etc. Right? We're coming out with a LiDAR depth sensor.
Yeah.
Momentarily, like a MEMS rotating mirror depth camera, etc. Right? You can use just a mono camera and that as well, and apply these algorithms right on top of it. We're not particularly wedded to our features or our tracker or anything like that. We just have a default set. But and adding in new things like our real odometry are relatively easy. But you know, we have to be sufficiently motivated to do something like that.
Yeah. But I think what I'm hearing is that certainly in terms of mounting this camera and putting it on the drone, people shouldn't just mount it on with some Velcro or hard tape.
Yeah.
It should be
So because we have all the data out, right? We give you the IMU data. You can actually look at the noise and decide, oh, look, maybe 1.5 G of noise on the accelerometer is too high. You know, we should consider isolating that. Put some sort of gel mount on there, or you know, something like that. Intel actually makes drones as well. We have ludicrously large drones that we sell commercially, and the teams there work really hard on getting the noise down for the accelerometers, etc. I mean, just because we rely on it so heavily, right? I mean, cameras, we're effectively mono at that height, and you just can't get scale from the image, right? So if you want to recover your path any reasonably with meters as its unit, then you need to measure meters, and the only device that measures meters is meters per second squared in the accelerometer. Right? That's the sort of intuition around this. So just the cameras don't measure meters, right? If you were in general, you just don't. So you can't get you can't accurately recover your trajectory without measuring
It is important though to think about the use case for ArduPilot, right? So when you're flying in open space and reasonably far from the ground, right, it's almost always going to be a situation where you can have a GPS and actually provide, you know, raw scale through GPS.
Yes.
So part of
that's the ideal location for the GPS, right? No multipath, nothing like that.
Yeah, exactly. Yeah, so the whole point here is to be able to deal with, you know, in a sense, I see the use case for ArduPilot is to extend the ability of all of these systems to operate when you're, you know, landing in a forest or you're going into an urban canyon or any of these situations where GPS becomes compromised, and you really need that precision to be able to fly close to a wall or close to a tree and not have a flyaway. So that's been one of the things that's been on my list personally, was to integrate GPS measurements directly into our filter, right? They're pretty low dimensional compared to the other things we're doing. This is one of the things I'm keen on doing with Paul and co in this community, is really integrating the VO into the existing EKF frameworks, but to do it in a really seamless way, so that, you know, we're not having resets of the VO that are putting offsets into the EKF, and having resets of the EKF, they're putting offsets into the VO.
This reset concept is the fundamental issue that everyone has, right? So generally, if we blow up, and we currently do, you know, it's sad, and there's no good way to restart again other than just starting from scratch, and, you know. And
so do you pass out a reset signal, so that, because I mean at the moment when you're
currently we output NANs, which you can detect using some algorithm,
right?
So, you know, I wish it weren't NANs, but it is. And so, you know, you can because we have this map though, we can keep the map in memory, and so when you restart, we can relocalize to the map. And
keep the map, but your bottom line is, with an EKF, you got no choice when it diverges, when it becomes bad conditions. You just got to nuke the covariance matrix.
So we actually don't really have problems with it diverging in general. The main problems we have are when you're sitting still. If you're moving, we almost never diverge. When we do diverge is when you're sitting still and the covariances go to 0 and our eigenvalues go negative and we blow up. That's really where it ties.
Yeah. Start again.
Yeah, I mean, no, and the way around that is a square root filter, and we're working on it, but it's hard to get it to fit in real time, right? So.
Right. Yeah.
Right. So I mean that guarantees that your eigenvalues stay positive the way the EKF expects them to be, right?
Mm-hmm.
But our algorithm is, in order to get this to run in real time, we care about every stage of the algorithm, every matrix operation, right? We don't implement the EKF in a naive manner. We try to optimize everything and reduce the amount of work we do at all costs. And so all of those go out the window when you switch to the square root filter.
Yeah.
So we'll see if we ever actually get it to fit in real time such that we can switch to that and get rid of what we know are our current failure cases.
Can we get the parameters, so the image parameters and such like, so we can try and set up an air sim with exactly the real sense flying around in it?
What do you mean the parameters?
So the fisheye lenses, the distance. Well, I mean, we can measure the distance between the cameras, but your actual lens parameters.
Oh, I think we have a spec for that. I'm pretty sure there's a. Okay. I thought that's in the extrinsics. We offer the extrinsics as one of the outputs from the SDK. So the location of the IMU, the location of the images, the cameras, they're all there. With the distortion parameters, which are not good, which I discovered from drone flight actually. I recommend recalibrating. But in general, we have all of that data available. So you should be able to create the exact thing and run on our recorded data, which is what I would recommend in terms of, everything we do is based on recorded data, internally, right? We try to find as many sequences that we can record where we have ground truth in some way so that we can, judge our progress. And you really it's the equivalent of our unit test, right? Is running across all the sequences that we have recorded over time.
Yep.
I've got a question here, if that's all right.
Sure.
So, hi, I'm Randy, and I'm one of the main multi-copter developers. And I put the T265 on a copter last week and flew it around. We had a GSOC student from last year, and also a couple other developers working on it, and it's beautiful, actually. The performance is fantastic. It just absolutely rock solid with the T265 on there, much better than with the GPS. So the stage that I'm personally at is just trying to help get it robust. So I just wanted to make sure that I understood how to detect properly when the T265 is losing its ability to provide a position or an attitude. And so I guess the things, or actually, I just want to make it robust. I just wanted to get your advice on the steps.
So the most important things are going to be don't rotate about the camera axis just because of this thing, right? And we're not going to die because of it, but it's just if you're looking out this way, don't rotate this way. So if you're downward facing, for example, don't spin the drone. You can trivially avoid it, just choose not to.
And is there a rate that I shouldn't spin at? The vehicle shouldn't spin at, or just don't do it at all if possible?
No. Rotate away. We can handle it just fine. It's just we're not as robust with it, right? Okay. So I'm just giving you minor optimizations that you can do, right? Yeah. So make dampening on the accelerometer, right? Make sure you don't have additional noise on the accelerometer. So you should look at you see the raw data in the little viewer we provide, or you can record it and look at it and graph it and see if you're getting a 1G of noise on the accelerometer, it's too much. See what you can do dampening wise to get it down, right? Fifth of a G, maybe, I don't know if I have any particular estimate on where you should be, but you should care about that. And the other thing is, motion blur is our current issue. Right now, we can't get our exposures quick enough that we don't get motion blur, and so we do. And so quick rotations in the other direction where you rotate this way give us motion blur. Mm-hmm. So those are our key issues, right? So that can be fixed with a little bit of effort. It just hasn't been our focus yet in terms of getting our exposure times down low enough, right? We were meant to work indoors. This system was designed to work for AR and VR contexts, right? Yeah. You're going to put this thing on a headset. And so we work in indoor environments where we have 50 hertz lights and 60 hertz lights that can cause beating in the images. And so we have some anti 50 hertz what is it called? Well, essentially filters to get rid of that, right? And so we set the exposure that's proportional to the some multiple of the 50 hertz in order to get away from that, to work in Europe indoors with fluorescent lighting.
Nice.
One day we would turn that off, and then we could get our exposures down low enough that we would have less problems with motion blur. But currently, that's our issue.
Is that something that can be done manually? Like we just disable that on drones?
I mean, there's settings, they don't do anything. It's currently broken, so sadly.
Jim, I have a question.
Sorry, I just want to finish off. So the other things that I heard you say that might help are providing like odometry input into the camera. So if we have velocities maybe from a GPS, in the case where we have a GPS, we could provide that in, and that might improve things.
I'm not sure that the GPS would be better than our velocity estimates ourselves, right?
Okay.
The places where it's where you have wheels that are actually closer to measuring velocity estimates, I think it's more useful than the GPS per se. The GPS is good on absolute, but not so much on velocity. I'd expect us to be more accurate than the GPS with respect to velocity.
Yeah, sorry, I said GPS, but actually, I guess I meant our EKF, which would be combined local IMU and the GPS put together. We get a,
I see. Then
so
maybe, yeah, I mean, you start getting dicey when you're mixing EKFs. That's my general take overall.
Yeah.
That's why we throw everything into one big old one, so that, you can at least, it makes it complicated and slow and covariant, with the monster covariance, but it means that we can not have to deal with all these issues of passing things between them where you don't know how much you trust each measurement, etc.
Yeah.
So you see, I think this is something that the community's going to deal with, right? So at the moment, we're looking at VO as an add-on solution to an existing.
Yeah,
I
think that's not the way to
VO
go.
solution, and so somehow either we need to move everything to a VO like you have, but that's really not a good solution for the community, right? Because lots of people just want to fly, and they won't have the vision.
So we can run with that, like we can run in the 3DOF mode and get orientation, right? One of the nice things about our setup is that the size of the Kalman filter changes dynamically all the time, right? As you pick up images or features, they come and go, different locations where you've detected features, and we can scale all the way down to just rotation. If the system is designed well, it can work for these other use cases as well, right? Turn on, like we can actually we can estimate image intrinsics inside the filter, etc., extrinsics, right? All the other tuning parameters. We don't usually turn them on, right? We turn them on a bit in the beginning to deal with, people banging their cameras around. But the fact is, once you have this generic framework for your EKF can change size dynamically in an efficient way, then you can throw in these other things and you can work in these other situations. You have different measurements depending on what comes in. So I would encourage you to go to rather than having these uncoupled systems, to try to put them together into one that supports just different sets of measurements philosophically.
Yeah, I mean, I'm keen on that, but I'm also aware that the reality of the engineering of the drone systems, you need to have your EKFs and everything that are reliable.
I know. So one of my goals for this was to make it so that it could be used in the loop for real-time control, right?
Yeah.
We worked really hard to make it so that it was low latency and high output rate. Now we have a couple teams at Intel that are, doing research on drones inside their lab, and they're saying our 200 hertz is not enough for them. They want us to go to 500. And they're saying that their controllers aren't working, blah, blah, blah. And so they can work with our 200, but they really wanted to go more. I heard you guys say 3,000, which we're not quite going to get to anytime soon. I believe we could get to 500. I'm not sure we could get to 3,000. But
Jim,
either way,
can
I think
ask a
putting
question?
them all into to one thing is something you should consider aiming for. Yeah, go ahead.
I was just wondering, can you rigidly couple the depth camera, the D435 with the T265 to get a more precise spatial alignment and tracking?
Yes,
Doing
we
a
do that
transformation?
internally, but we don't have a way. So yes, you should. we actually give a STL file for a mount so that the intrinsics will be just known and you can enter them in. Like we give the extrinsics if you use our mount that you can 3D print, so that you can attach the two together so that you can use the depth. You know, you can create a 3D model relatively straightforwardly. I don't know how accurate it's going to be overall, but it'll be pretty good because you can combine the pose from the T265 and the depth from the D435-5, for example.
Right. That's what I was thinking could overcome some of those issues.
Yes. In particular, we have modes internally where we can use the depth from the D435 in our filter, for example, right? But it turns out the depth from the D435i is pretty latent, and so we don't even export that generally. Right. We're trying to make this a real-time system, right? Our goal was for you to be able to do the feedback, as I said before, right? Your actual path planner should be able to use us in the loop. That was our vision. And to do that, we can't wait around for the depth over USB or whatever we were doing, right? Just at least the last time we tried it, the latency was too high for us to be happy with
it. Treach, are you happy with this conversation? Do you want to move on with the
great.
conference?
I mean, and Olivia in the side chat has been saying he's fine about it going on. So we probably finish up maybe 25 past the hour. So in a couple more minutes, if there's a few more questions. It's been a fantastic conversation. I greatly appreciate you coming along as well, Jim. Really appreciate that discussion. And I imagine there'll probably be some follow-up questions from some of the people who are working with the 265 really closely. So are there any more questions now for either Rob's team or Jim before we move on?
Yes, Jim, hello, this is Patrick. We had a couple of chat on the GitHub since a year now. And one of the first request was, would it be possible to have a stripped down unit with just a plain serial port on it so we could use it on lower type of...
Yes, of course it's possible, as I said before, but it's unlikely to happen. So the chip we have has a serial port, and I'm sure we could get data out of it pretty easily, but getting it all wired up and then different BOM, etc., is not going to happen, right? Unless you tell me you're going to sell some large number of them, right? Already this product doesn't sell enough for anyone to be happy. I encourage you all to make an actual product and sell lots of these in order to keep this project alive.
During this thread, you saw that I've been able to make it work with a small size computer like the Raspberry Pi 0 or the Banana Pi 0, so it's worked quite good. The tricky question everyone asks, can you have a patch available for the Movidius boot process?
Yeah, so we have this issue where the power to the Movidius comes on at a different time compared to the USB. Like, so there's a power sequencing issue with respect to the USB and the Movidius. Again, this was meant to be used in some, wasn't meant to be released to the world the way it was in the end. We thought we could work around it, but now we see that everyone's running into it. And so pretty much you have to cycle the power on your USB port in order to deal with the issue when the bootloader detects the wrong USB version, essentially. So sometimes if your USB power comes on after the Movidius comes on, the bootloader on the Movidius chip thinks we're in USB 1.0 instead of 2.0, and we can't talk to it ever. It's a sad state, but a lot of devices like the Raspberry Pi, you can actually control the power on individual USB ports. And if you cycle that, you can turn it on and off. USB Hub Control is an open source program that you can use to do this. It was on my list to integrate this into LibRealSense so that it would just do that if it detected it, but it's not going to happen.
This is actually what we have done so far. Maybe Randy can comment on that.
Yeah, it works. It totally works. So the suggestion to use UHub CTL works on a Raspberry Pi. So yeah, we've got an image now that does it automatically, so the user doesn't have to worry about plugging and unplugging.
Yeah. Yeah, I wish that were not the case, but sometimes there are bugs.
All right. Well, this has been absolutely fantastic. Thank you so much, Rob and Jim and Peter and Ryan. It's been a brilliant presentation and a lot of very interesting discussion. So I think a round of applause for our speakers from this morning.
Yeah, fantastic.
Thank you very much.